Okay, let's begin because this is my last talk for this school. Okay, so far I could show that actually there exists a theory called quantum chromodynamics that has the right property to describe the physics of hadrons at very high energies. Okay, that's the summary. It contains a right coupling constant which behaves exactly the way we want. Okay, so that's good news. Let's see whether we can actually make more sense out of this theory, and in particular in the context of pattern model, because I left pattern model in the morning. Okay, I'll have to go back and see what are the modifications that I can do to the model that I wrote down, so that the QCD can be successfully used in such models. Okay, so let's go back again deep in elastic scattering. Okay. And this, I showed you this cross section. Okay, so this one I had written down as, for example, if I'm interested, let's say for convenience, I chop off this part. Okay. I don't mind, because that was only overall factor. Okay, and call this gamma star with Q. Okay, and this is the process I'm looking at actually. The cross section is proportional to this. I do everything. So this cross section, sigma gamma star P, okay, which is a function of Bjorken's variable, and then the scale Q square in pattern model looks something like this. A equal to quark, anti-quark, and gluon. Okay, now I'm bringing this gluon into this picture. Okay, because if I assume my theory is, Ty, this is my pattern model. So Y, T sigma, gamma star, A. Okay, so this is Y, Q square, XBJ. Okay, so I just added this one more person in the train, because I'm going to use QCD to understand this formula and see whether there are any modifications to this formula actually. So I need to include along with the quarks and anti-quarks, I need to include gluons also. Okay, and correspondingly the cross section for gamma star interacting with A will have an interaction of photon with the gluons also. Okay, you'll see that this can happen actually. Okay, as I said, this quantity is called PDF. I'm not calculating this. Okay, but this is pattern level cross section. But I said it's calculable because it is an interaction of, it describes how photon interacts with A. Okay, photon interacts with A electromagnetically. A is a quark. If it is a quark, it will interact electromagnetically. So that sigma that we have written down is calculable in perturbation theory. So let's try to do this actually. Okay, now let's see whether assume this formula, okay, as if it is given to us. Okay, and see whether QCD we can actually calculate this quantity explicitly, order by order in perturbation. So I'm going to use perturbation theory. Why? Because I'm studying in a region where alpha S, coupling constant, is small at high energies. Okay, so I can very well use, perturbation theory. What does perturbation theory means? If you want to calculate this gamma star A quantity, I can calculate them as series expansion in strong coupling constant. Okay, gamma star A, 0th order term plus first order will be AS of, because this coupling constant depends on mu r square. So this is sigma 1 gamma star A, okay, order 1, okay, it will all start depending on the scales, etc. This is a series expansion that you can do. Okay, this is the leading order term in the expansion. This is the first order. In quantum mechanics is what you do, Born approximation, first term, second term, in couplings. Okay, so this is very straightforward to do it actually. Now, what are the diagrams that would contribute actually? Okay, I'm going to list some of these processes. Okay, so this leading order level, AS power 0th order. Okay, you can have a diagram where a parton type A scatters off with this photon gamma star. Okay, this is one amplitude that you can write. Okay, now at AS square level, AS level, okay, first order term, this is 0, this is 1. You can have term like corrections to this like actually. A gluon exchange between this initial quark and the final quark. Okay, so this is A, this is A, this is gluon. This is typically a term that can appear, contribute to this sigma 1. Okay, what else you will get? You can also have term like this, where gluon can be produced in the final state. This is gamma star, this is Q, this is Q. You can produce a gluon in the final state. Okay, it can come either from initial leg or final leg. So the price that you pay here is actually the strong coupling constant GS here. Okay, when I square this diagram, because these are two amplitudes, this will be proportional to GS square, which is AS I call. Okay, so you can have diagram of this kind. What else you have? You can also have at this order, photon interacting with gluon through this pair of quark antiquark. Okay, this diagram. Okay, this is quark, this is an antiquark, this is a gluon, this is the gluon. Again, when you square this diagram, this will be proportional to GS square, which I call AS. Okay, so you can have bunch of Feynman diagrams at every order in perturbation theory that is going to contribute to this process actually. Okay, so if I want to use this formula is actually as it is. If I don't include anything, it's of no use actually. It's only leading order. Okay, it is not going to describe even the existence of gluons. Okay, so I need to actually worry about improving this formula. Okay, the only improvement that can come is actually make a series expansion in strong coupling constant, calculate now order by order in perturbation theory. Okay, this we can do step by step. Okay. Okay, so now what would the formula look like actually? The formula would look like sigma. Okay, this is first there will be a contributions coming from quarks and antiquarks, etc. Okay, so integral dy, okay, f a of p y. Okay, this will be multiplied by contributions coming from there. Okay, so the leading order contribution, if you work out, it will be simply proportional to 1 minus z, where I'll write down what z is equal to. This is xbj by y or whatever. Plus Okay, so there will be a whole lot of term that is coming from this kind of diagrams actually. Okay, so I'll just put this within the bracket. What are the diagrams that it can contribute? Like this. Okay, and this. Okay, these are the diagrams that you need to calculate and put it here actually. Okay, this is order alpha s. Okay, now you can have a gluon contribution. So I'll have to add a term which is dy f gluon and proton y. Gluon part starts at as of mu r square. Okay, times this diagram. Okay, so this how it looks like actually. So if putting it explicitly, you find that a series expansion of this kind, where you have a one gluon exchange, one gluon emission, and then the photon interacting directly with gluon, because gluon is, photon is not, interacting with gluon directly, but it can interact through quark or anti-quark. So these are the typical diagrams that you can get. Of course, I'm not adding terms which are order a square. Okay, those things I drop for a simplicity. Okay, now let's see, what are these contributions, how the answers look like actually. I'm doing this exercise because I'm going to show you something very interesting about these functions actually. Okay, so let's put this also for simplicity. This is sigma 0 here, because it's not just constant. Okay, where sigma 0 is simply 4 pi eq square into 2 plus, in dimension regularization, it will be 2 plus epsilon. That's the answer to this. Okay, now I'm going to write down certain answers. Okay, if I calculate this diagram, for example, okay, this is gamma star. This we call gamma lambda, which is minus integral d and k by 2 pi all power n. Okay, and then this is gamma alpha ta gs k slash gamma lambda. Okay, it goes on like this actually. Okay, I'm just going to tell you something interesting about it, because I cannot teach QCD without, because of the coupling constant, you have this quantity divided by, whole divided by this propagators, k square, k minus p2 whole square, k minus p2 plus p1 whole square. Okay, typically this results for diagrams would look like, the string of some gamma matrices and vertices and propagators. You need to do this integral actually. Okay, I don't think I'll be able to do this integral here, but I will just write down the answer, and you can also try at home. If you do Feynman parametrization and use this formula, 2 pi whole power n in n dimension, k square power a, k square minus c power b is equal to this formula. If you use, this is also derivable, but I'm not deriving here, n by 4 c power a minus b plus n by 2, okay, gamma of a plus n by 2, gamma of b minus a minus n by 2 divided by gamma of n by 2, gamma of b. Okay, if I use Feynman parameterization to do this integral, I will end up with the simple scalar integral. That scalar integral, if you substitute, you get an answer which is something like this actually. Okay. So this cross section now contribution would look like sigma hat of 0 times coupling constant mu r square times, I've got color factor here, times minus q square by mu r square power epsilon by 2 times minus 1 by epsilon square 16 plus 12 by epsilon minus 16 minus 2 theta 2 delta 1 minus z. Okay, this is how it would look like actually. So this entire one loop calculation, if I just do a couple of manipulations, you can show that it is something like this. And it is a divergent quantity, as you can see. In the limit epsilon goes to 0, d is equal to 4 dimensions. Still okay. Okay, it is only part of the computations. Okay. Now we can proceed exactly in the same way. Okay, to calculate these remaining terms actually. For example, if I try to calculate this quantity plus this amplitude, okay, you can write down the amplitude actually. Okay, the amplitude would look something like this. I call this quantity as sigma 1, real radiation. Okay, it will be two body phase space because you have two bodies in the final state. Okay, averaging over the color factors and spins. Okay, and then you have two amplitudes, m1 plus m2. Okay, multiplied by polarization tensor lambda. Okay, whole square. This is all you need to compute actually. So two amplitudes you write down here. Okay, square this amplitude to the phase space integral. Okay, so I don't know whether I should do that, but I will just illustrate how this can be done actually. So to do this, you use this parameterization. For example, incoming parton you parameterize as S hat plus q square into 1, 0, 1, and then this momentum q you can parameterize as square root of S hat S minus q square, 0, 0 minus S hat plus q square. This is just a two body phase space parameterization. P3 you can parameterize at S hat by 2, 1, 0, cos theta. Okay, if you do this, then this dps2 would look something like 1 by 8 pi q square into 1 minus z or 4 pi z or epsilon by 2, 1 plus epsilon by 2. Okay, dy into y into 1 minus y power epsilon by 2. Okay, this is how the phase space would look like. And all I need to do is actually evaluate the matrix element, multiply this phase space, and perform this integral y. Okay, that is as simple as that actually. Okay, so the answer to this process would be something like this: m of 1, a real part, is sigma of 0, as of mu r square. I'll write down what is the answer to this. This is q square by mu r square power epsilon by 2. Okay, this is 16 by epsilon square delta 1 minus z plus 1 by epsilon pqq some function of z plus fq of real of z actually, something like this. I'm not explicitly writing down the expressions because I'm not going to use it anywhere actually. So if we calculate those, 2 going to 2 process in QCD by just substituting all the Feynman rules, performing this phase-space integral using this parameterization, you will end up like this actually. There's an answer like this. Okay. Now you can see there is a result for virtual contributions, this kind of diagrams, which contribute at order alpha s level, which is proportional to minus 16 by epsilon square by plus 12 by epsilon. And you get a very similar answer when you consider the real emission process, which is plus 16 by epsilon square plus 1 by epsilon times p. Okay? If you add these two together, you see that 1 by epsilon square cancels actually. Okay? You will know if you are really serious about this kind of computations, you go back and check it, and also you'll have an understanding of this, why this cancellation happens. This happens simply because there's a famous theorem in field theory called Kinoshita-Lee-Neuenberg theorem. It says all the soft singularities, okay, in any sensible field theory has to cancel among themselves actually. Okay, if you sum all the degenerate states. It's just a statement, not going to prove anything, but it's consistent with that theorem actually. It's called KLN theorem. So epsilon square, they cancel actually, these poles. Okay, but 1 by epsilon doesn't cancel. Okay, so I have reached the stage that I can finally write down the contributions purely coming from the quark initiated process, namely the first line of this expression actually, this expression. So you consider this part. I want to write down what is the answer to this, and I will write down the answer for the second line one by one actually. Okay, is this okay? So all I'm trying to tell you is actually that sigma can be computed order by order in perturbation theory using diagrammatic approach. Okay, and the method goes something like this actually. Write down Feynman rules for the corresponding diagrams, perform phase-space integrations the way we did it for the form factors, and you get an answer actually. So it's not very easy, but doable actually. Okay. So this computation that I'm talking about was done in 1970s, just after the QCD was invented. Okay. So now the full answer to this, okay, let me write down the full answer. It would look something like this. If I am considering quark initiated process, XBJ, it's considered only the quark initiated part, actually, the first line. Okay, first line. I'll come back to the second line later. So first line would be sigma q is sigma hat, and then later on I will add that also. Is fq of xbj. Okay, I'll tell you what this symbol means. Okay, so I've written something here. Just wanted to tell you what this notation means. Suppose if I have f of z, g of z, it simply means this is dy by y, okay, z to 1, f of y, G of Z by Y. It's called convolution. So instead of writing integrals after integrals, you can actually introduce some notation called convolution and write the integral in this notation, convolution notation. So what I have done is actually I just added contributions coming from various parts. Okay, it just boils down. You don't have to worry about too much of indices and things like that. All it says is actually you can write down a part as which depends purely on this 1 over epsilon, and a part which is finite as epsilon goes to 0. Okay, if you want, I can just tell you what it means, what I have written actually. Suppose you have a expansion. Hope you can see me, or maybe I can do it somewhere else. Can you see? Everybody can see? Okay, so suppose I have a term. Okay, say f of x is equal to 1 plus let's say a is some simple parameter a of 1 by epsilon plus g of g. Okay, suppose I have like term like this. I can always write this as 1 plus a by epsilon into 1 plus a into g. Okay, dropping a square term, isn't it? As long as a is small, you can write it as a product of these two terms. Okay, if I am neglecting all the terms of order a square term. Okay, so f of a can be written as f of 1 plus a by epsilon times 1 plus ag plus order a square term. Okay, so this is a very good way of writing, epsilon dependent part here and epsilon independent part here actually. So that is all I have done actually. So I have calculated some quantity. That quantity contains, mass of the poles 1 by epsilon and finite part. Okay, that you can write as, part which contains only the pole 1 by epsilon and a part which contains no poles, finite. Okay, so the divergent quantity now is written as product of a divergent part times the finite part. Is this clear to everybody? Okay, it is as simple as this actually. I know that this is a divergent quantity. I've just factored out this up to order a square. Okay, this is simple mathematics. Okay, so this is what you call factorization. Factorization of collinear singularity. This 1 by epsilon comes from collinear partons. Okay, so it's not very difficult to understand this. In a scattering, if there are two massless particles, okay, if they produced collinearly, such a configuration is divergent. Okay, it does not exist in nature. Okay, it's collinear patterns. Okay, unless something is included in that process actually. Okay, so this collinearity is actually a property of collinear singularity is it's a property of massless particles. Can happen with electrons also. Electrons are massive, so you don't see two electrons becoming collinear and giving you any difficulty. In the case of quarks, we consider very high energies. You drop all the masses, hence these collinear singularities are sort of present in these computations. And this 1 by epsilon that you see signals the existence of such collinear singularity in such computations. For example, in this diagram that I've written down, when this pattern becomes collinear to the initial quark, or this pattern collinear to the final state quark, you have these divergences. So that is the divergence that I've written down here actually. So the partonic cross section that you compute contains divergences, and that can be factorized in a universal way. And this function is called Alter-Rayleigh-Parisi splitting functions. Splitting functions. Okay. This tells you the probability of splitting, this collinear pattern splitting actually. Okay. So this is the meaning of this, scattering cross section. It's not just we calculate some Feynman diagrams and get, some expressions and then we are happy, but we also wanted to actually look at what are these pieces and what physically it means actually. So all you need to remember here is actually that it is proportional to 1 plus alpha s. It's coming from the first order. There's a pole term containing this splitting function, and this entire thing is multiplied by some finite remainder, like here. This is a finite remainder, which is multiplying here. This is a singular part, this is a finite part. So it's a factorization of singular part times finite part. Okay? This is all you should remember. So the cross section, partonic cross section that you compute, nicely factorizes into a divergent part containing collinear singularity times a finite part, which are finite, when regulated is taken to be 0. Is this clear to everybody? Good. So this is the contributions coming from quark. So I need to work out what is the contribution coming from gluon. Okay, it's exactly like this. Okay, this is the second line that I have written down here. Okay, and the process also known. There is a photon interacting with the gluon through a quark loop. Okay, and you can work out and show that it will be also proportional to sigma hat g, and then this corresponding PDF will be f hat of g x bj. Okay, convoluted with, again it has a similar factorization structure. So it will be proportional to as of mu r square because it starts at order alpha square, and then you have a term which is, let me just write down. I can't remember what I had written down. Okay, so convolution times this 1 by epsilon times pqg, this is another function that appears here, plus fg of z. Fg is some calculable function. So again you can see this entire partonic cross section is simply this proportional to coupling constant times a pole plus a finite part. That's all. So this whatever I wanted to do can be actually put it in 3 lines actually. This is the contributions coming from quark part. This is the contributions coming from gluon part actually. Okay, so far so good. Okay, now this is the answer. Okay, I did nothing except putting all the Feynman rules, did some integrations, and written it in a form that looks reasonably good looking. Okay, but unfortunately this formula, if I take it as it is, okay, it's not going to give me anything interesting, because if I tell this is my answer, I'm going to put it along with the original formula, then nobody will buy it actually. Why? Why nobody will buy? If I send it to a journal, it will be rejected actually. You know why they will reject it? It depends on 1 by epsilon actually. Okay, it contains 1 by epsilon. So it is useless actually. All this exercise, after 1 hour of doing this computation, you end up with answer for this quantity, calculating these diagrams, became an answer that is not acceptable to anybody, because it depends on 1 by epsilon. There's no. So the first thing that will come to your mind is, okay, maybe I'm doing it for the first time. I might have done a mistake. Okay, then again go back and check it actually. You'll find that the answer is correct, and there is a 1 by epsilon 4. So let's believe that the calculation is correct, done it correctly. Okay. So what is the resolution to this problem? Okay. This is not the board I wanted to see. That's the board I wanted to see. So the answer that I have is actually not useful in the form that I have written down actually. Okay. It contains 1 by epsilon singularity here, 1 by epsilon singularity here. I cannot take epsilon goes to 0. I need to take, otherwise, it makes no sense. Epsilons are introduced to regulate the divergences, not to keep it with you. Okay, it is only regulator. Regulator should always be taken to its natural value at the end of the computation. If I do it, I am going to get. So it is a disastrous situation. Disastrous. Okay. So how are you going to resolve this actually? Any idea from audience? Because it's my last track, maybe you can speak to me. Any suggestion? If you are looking at it for the first time. Sorry? Definition of what actually? P. P is actually calculated quantity actually. We have calculated that quantity using this method. There's a definite answer to that actually. I cannot change that actually. If I get to 22 by 3, I cannot change to anything. Renormalization, what you do actually, you don't change any finite quantities, no? P is a finite quantity. So you cannot change. You are very close to the answer, but sorry? Yeah. Yeah. So you are saying that, instead of calculating for one particular energy, calculate for 2 energies and subtract it actually. You can subtract it, but somebody wants to calculate at 1 energy. That is an observable, because deep inelastic scattering can be done at a very specific energy and get a sensible answer, no? Okay. Any answer? Very close to what he said actually. Oh, sorry? Put the counter term actually. From where I can bring the counter term actually. Very good. There are many close answers. Let's see whether I can do one thing. Okay. Now I will have to look for some, the morning, not in the morning actually, in the previous lecture, I mentioned that, you have a QCD Lagrangian. We have many terms like fermionic fields, gauge fields, coupling constant. I rescaled all of them actually, okay, and demanded the Green's functions are finite and fixed all the constants, okay. Here, what is that is left that I can actually meddle with, okay. The only thing that not only one, few are these PDFs, FAT. FATs are actually very innocent guys sitting with this, with this expression all along actually, right? Is that correct? FAT. FATs are just simply some non-perturbative quantities I called actually. It has an interpretation that it's a probability of finding. But I don't know what that function, how it would look, is going to look at. I don't even know it's finite or infinity. Okay? It is like, there's wave functions in quantum field theory. Gauge fields or fermionic fields, coupling constants. So now I'm going to use this freedom to redefine this FAT. Okay, that's what somebody said actually, something like counter term or absorb into something. So I'm going to redefine this FAT in such a way that the divergence can be, sort of removed. So this is one way of renormalizing. It's not ultraviolet renormalization. This singularity that you get is not coming from ultraviolet sector, it is coming from collinearity of the partons in the final state. So you need to actually remove them. You don't need to remove them actually, but there is a mechanism within the system to actually take care of that. What is the mechanism? Suppose I redefine this. I combine this and this together and write it as a new pattern distribution function. Remove the hat. Okay? Then my answer will be independent of 1 by epsilon. Okay, let's do what we can do. I will use this part of the board so that I can actually easily copy from here to here. Okay. So I'm going to define a new PDF in the following way. So that's the first step. So how I'm going to define new PDF? Let me define this way. If I define FQ of Z of mu r square equal to F hat of Z Q times delta 1 minus Z plus AS of mu r square times 1 by epsilon PQQ of Z bracket plus FG hat of Z times AS of mu r square times 1 by epsilon PQG of Z. Okay, this is my definition. Okay, am I allowed to do this? I'm just calling the sum of these two terms is simply this f of q without hat. I'm not putting a remove hat from this. Okay, this is just a definition. If I do this, okay, now this formula, if I add these two, I can express everything in terms of this fq and fg. Is that correct? So if we do this exercise, you just put this, drop all the terms that are of order a square, higher order terms. Okay, then this full cross section would look something like this actually. Let me just write down what is the answer. So you can write down this, f of at is gone, okay, xbj. I introduced some scale here, mu r square, because right hand side contains mu r square, I need to introduce mu r square. Originally that f does not contain any scale dependency. Okay, so this will be as of mu r square times, okay, delta 1 minus xbj plus as of mu r square times half of pqqq, a log of q square over mu r square plus f of q of z. It's finite. Okay, this is the first term plus fg into xbj mu r square convoluted with as of mu r square into 1 by 2 pqg of log of q square over mu r square, okay, plus fg of z. Okay, so this is my answer actually. So what I did was actually I combined this divergent part and call that part is equal to fq and substituted back in the original formula. Okay, if you do this, then I get a formula where 1 by epsilon is gone. But instead of f hat and fq hat and fg hat, I have two terms without hat, but there is a scale dependency mu r, because by definition this entire quantity should be function of mu r square actually. Okay, so this is in the limit, epsilon goes to 0. Okay, I don't know anything about this side. I call that in the limit epsilon goes to 0 is this quantity. So these are called renormalized PDFs. Okay, not in the UV sense. It is in the collinear sense. Okay, infrared renormalization, if you want to call. Okay, so these are called renormalized PDFs or collinear mass factorized PDF. Okay, something like this you can call. So I get a cross section now which is finite. Only difference is actually instead of f hat that I had written down in yesterday and today morning, now it's not f hat, it's a new function which explicitly depends on the scale mu r. Okay. Now, bell should ring in your head. Okay. Whenever you do this renormalization, rescaling, okay, there will always be renormalization group equation, right? When I did this coupling constant renormalization, I found the coupling constant evolution can be actually predicted, right? You agree? So morning exercise, not morning actually, this last lecture when I discussed about coupling constant evolution, I said, if you renormalize, UV renormalize your theory, you scale all the parameters of the theory, all the fields of the theory, and the bonus is actually that the coupling constant, mass, etc., they start depending on the scale, then they satisfy renormalization group equations. And by solving that, you could actually show that coupling constant evolves and it falls off to 0 at very large energies and so on and so forth. Okay. Now we have a very similar situation. Okay. We have renormalized our, these PDFs that appear here. Okay. And this renormalization should also give you a renormalization group equation. Isn't it important to actually study that? Is this clear? Okay. So let's see what that renormalization group equation. You will be pleasantly surprised that it is something that is familiar and you must have heard about it many times. Okay, so let me do that. Okay, so I have an answer to this problem completely. That is the first achievement, that I can calculate, this expression. It turns out all I need to do is actually remove this part and put mu r square, okay, and I have some finite results for this. It's finite, and similarly here half of PQG of Z log of Q square over mu r square plus FG of Z. Okay, so this is a finite answer. Okay, everything is sensible. I can use this formula for some reason. I will come back to this little later. Okay, because Abhay showed something very interesting about scaling violation and things like that. I'm going to show something using that actually. That's the first part. Second, that the PDFs are okay, good. So I wanted to say one more thing actually. If I don't tell, because it's being recorded, I don't want to be wrong in a recorded lecture. Let me, make it more precise. Okay, so far I used renormalization scale mu r for, renormalizing my UV sector. Okay, but I merely actually continue to use the same scale to factorize. Okay, there's no reason why the scale that I used here is same as the scale that I used it to renormalize my UV renormalize my theory. Okay, so I can be completely more general. Instead of renormalizing at mu r, factorizing this kind of things, I can also do it at some other scale mu f. Okay, this is just a point. I don't want to bring in here because it will make it very complicated, because there will be another scale, there will be logs of that scale, and so on and so forth. Okay, just assume there is no reason why I can choose that mu scale to be mu r. Could be completely different scale. Is this point clear? Okay. So that scale is called factorization scale. So I'm very quiet about that factorization scale because if I put it, it will become a little more complicated actually. But otherwise it can be done systematically. So in principle, this formula will have mu f here. Okay. This part will have a mu f and mu r dependency. That's the correct way of putting it actually. So this will have a mu f dependency, and this will have mu f and mu r dependency. Is it okay? So that scale is called factorization scale because it is coming from the infrared sector. Okay, good. So that's one thing. Now I wanted to show, as I said, that by redefining your pattern densities, you can get renormalization group equations. How? Okay, I take this formula. Okay, so let's assume that scale is something like this, f of so I have renormalized my okay. This is our definition of this quantity, right? Everybody agrees to this formula? That's the shortened version of the same thing that I have written down here actually. It contains 1 by epsilon times some quantity. Okay, there is also, where is that actually? Yeah, PQQ, this quantity. Okay, I have rewritten everything, but only difference that I have put is actually this mu r because I don't need to have the same scale to renormalize. Okay, I've done this correctly. Okay, and let's see what happens. So the left hand side depends on the scale mu f. Right hand side only the brackets contain scale dependency. Okay, this f hat which I had written down originally in my original pattern model does not have any mu f dependency. Okay, which means if I differentiate this mu f square dfq of d mu f square, okay, z comma mu f square, okay, nothing will happen to this if I differentiate this. All I need to do is actually I have to only differentiate these coupling constants, correct? Okay, so if I do this, then I get f hat of zq multiplied by, so it's only act on this part, as, so it is mu r square, mu f square, df by d mu f square, as of mu f square, times 1 by epsilon times pqq of z. This is correct? What is the second term? Second term is fg hat z convolution mu f square d by d mu f square as of mu f square 1 by epsilon pqg of z. Okay, and I am dropping all the higher order terms. What is this quantity? This. If you look back, look at your notes back, actually, you know what I have written. You see that log of mu r square d by d mu r square. Can anybody tell me actually what is the answer to this? So it's beta function only if you take epsilon goes to 0. I've not you have to keep all the terms. Okay, so the first term is actually epsilon, no? Epsilon times as plus some quantity. It starts with epsilon. I don't know whether you have the notes. You can just look at it actually. So it's proportional to as, and then it starts with beta 0 and things like that. Only if we put epsilon is equal to 0, it is This is absent. But in the middle of the calculation, I should not put epsilon is equal to 0. Suppose you are calculating a huge quantity, okay? And then you are doing, epsilon expansion. So you should take epsilon goes to 0 only at the end of the calculation. You cannot just arbitrarily, wherever epsilon you see, you should put 0. Okay? Because if I substitute here, you see this epsilon and this epsilon is going to cancel. Correct? Agree? So if I take this, and this is epsilon times AS. So this epsilon and this epsilon will cancel, we get finite term. Okay, similarly, this is epsilon times AS, this epsilon and this epsilon will get. So this renormalization group equation, okay, simply gives you this d f q z comma q mu f square d mu f square equal to pqqq of z as of mu f square times f hat of z, okay, plus, let me just write it down. Epsilon dependency is gone actually now. Plus as of mu f square pqg of z fg of z plus order a square. Okay. This is what you get, a differential equation which looks very similar to this renormalization group equation. Okay. This tells you how it evolves. Okay. Now, if I again iteratively put back f hat, okay, this will be like f of mu f square. This will be f of mu f square. Okay. Then this as of mu f square will be the higher order term, because I can iteratively substitute the solution actually. I can substitute the solution back here. You find this is the equation that you will get actually. Okay. So it tells you how the renormalized PDF evolves as a function of the scale mu f. Okay. It's like a renormalization group equation. Instead of beta function here, you have some splitting function. Okay. And this equation has a very famous name actually. Huh? What is that? Loudly. De-Glap equation, yeah. It is called Altarelli-Parisi or Duck-Chixler, Altarelli-Parisi, Gribov-Lipato, De-Glap evolution equation. Okay, it tells you how the PDF evolves according to the scale. Okay, so I can write down actually the correct one. Okay, so if I calculate d by d mu f square, fq of d mu f square, fq, fg, it will have this structure as of mu f square, a matrix pqqq, pqg, all of them are functions of z, pgq of z, pgg of z, times convolution. Okay. So evolution of PQ is controlled by two splitting functions, PQQ and PQG. Evolution of FG, gluon distribution, is governed by FGQ and FGG, PGQ and PGG. These are called splitting functions actually. Okay. So PQQ actually would come from diagrams like this. It is the probability of finding quark in a quark. Okay. This is this. And PQG is actually finding a quark in a gluon. Okay. PGQ is finding a gluon inside in a quark. That's the probability. And similarly, PGG will be finding a gluon in a gluon. So these are all just some probabilities. So square of this will contribute to PQQ, square of this will contribute to PQG, square of this will contribute to this, square of this will contribute to this. Okay, this is all physically expressible. So you have something called Alter-Rayleigh-Parisi evolution equation. Alter-Parisi or D-Glab, or simply renormalization group equation. Okay, it is simply renormalization group equation coming from collinear sector. Okay, so this is all it means actually. Okay. Original derivation of Alter-Rayleigh-Parisi is not like this, but it has some diagrammatic method and explicitly showing some it has evolution. But this is just a modern version of Alter-Rayleigh-Parisi evolution equation. I just wanted to motivate how coupling constant evolves in quantum field theory and how PDFs evolve as a function of scale using some process actually explicitly. I'm not using any specific setup or a framework to get this actually. I get it by just looking at certain processes. Okay, it's like if I want to go and find out where Bombay is, I take my car and travel and find out. Okay, without using Google Map. Okay, this is just an exploration to get what we already know in the literature by working out things consistently without getting scared in between. So that's all I did actually here. You calculate a deep inelastic scattering. I started from this bare naive pattern model, and I take QCT as my theory of strong interaction and calculated the cross section. I found there were divergences, and I can resolve them by absorbing them into the PDFs. In the process, I get a new definition for PDFs. And I used this idea that I used for renormalization group equation for coupling constant and applied it here. And you can show that that application gives you a differential equation. And that differential equation is nothing but Alter-Rayleigh-Parisi evolution equation. So summary, that this pattern model formula that we have here, okay, which is finite, okay, we have a complete understanding of these PDFs, how they evolve, even though we cannot calculate them. Okay. Now I'll make my statements more precise. That PDFs are not calculable; they are extracted from the experiment. However, the evolution of PDF, okay, given a PDF at some scale, I can tell to anybody how it would look like in some other scale. Even though I don't know how to calculate the PDF as such. It's like, I cannot make a person, but I can actually tell how he will behave. Okay, it's like that actually. So I can actually use this formula, and solving them, I can actually tell you how PDF evolves with respect to scale, how it would look at various scales. Okay, if somebody says U-quark distribution is like this, the first question that you should ask is actually at what scale that it looks like this. Because if you change the scale, the PDF would look completely different. Okay, so it depends on the scale at which you look at, measure these quantities. So it's a very, very powerful equation. Okay, and it tells you how PDFs are different at different scales. Today, Abhay was talking about the spin content of the proton. Those are also related to the PDFs. They are called polarized PDFs. And those PDFs are extracted from experiment. Okay, that carries very valuable information about how spin content of the proton. Okay, now the value of that depends on the scale, because they also satisfy some renormalization group equation. And when somebody says U-quark carries almost 0.1% of the proton spin, okay, it is at some scale actually. Okay, at that scale, probably that contribution is only 1%. Okay, but only theory will tell you where exactly, which scale it will be large, which scale will be small actually. Okay, so being small, you should not be worried actually, because it is in that particular scale. For example, if somebody says half of the proton momentum is carried away only by quarks, it just means that actually in that particular scale it's half of them. Maybe there are some scales at which most of the proton momentum is shared by the quarks alone. Gluons are left alone, carrying nothing. Okay, all these statements are all dependent on the scale at which you extract them. Okay, so this is such a powerful equation that tells you that you cannot make an absolute statement that proton carry, quarks carry this, that, all that. Okay, you can only make statements about their contributions in some scale. That's one point that I wanted to make. Two, don't be too carried away by the fact that these are all two physical quantities actually, meaning they are not like laddus you can eat, meaning that these are mathematical constructs actually. In quantum field theory, charges, coupling constants, or PDFs, masses, all the parameters in the theory, okay, they are all actually defined in a particular scheme. Okay, here I use dimensional regularization and I defined these PDFs in that particular scheme. Okay, so the schemes are the ones that defines a coupling constant, strong coupling constant. If you go to PDG, you can see the coupling constant is actually given as 0.118 in MS bar scheme. Okay, there is a some subscript attached to or superscript attached to this coupling constant called MS bar. That value is the value extracted from the experiment using a formula computed in MS bar scheme, which means it is a very specific scheme, result from a scheme. Okay, so giving too much meaning to that, it is a very physical quantity, 118 is actually great number and things like that, it's all meaningless because it's a scheme. Somebody can come and say, okay, I don't like MS bar, I'll use Mr. Ravindran's scheme and get some number like 0.113. Okay, you should not be too surprised. That's also a good number, not because it's Ravindran's. It is simply because every scheme is equally interesting, important. That's one point. Why I'm saying this, it is the same spirit when I say this is a PDF which describes partons inside the proton. They are in quantum field theory, they are defined in a particular scheme. I used MS bar scheme to define them actually. Somebody must have used some other scheme. Instead of absorbing 1 by epsilon, they could have absorbed 1 by 1000 or 500, 20,000 and defined my new PDF accordingly. Okay, so the definition of PDF changes. Okay, and if you change the definition of the PDF, then if somebody says proton spin is carried away by gluons, someone else can come and say that, oh no, sorry, that is wrong, can be carried. So all these statements depend on the scheme in which you actually define these quantities. Okay, they are not physical quantities. Only the one that he wrote down, the sum of all the contributions, like delta sigma, delta G plus the angular momentum contribution of both quarks and gluons, if you sum them all together, that is the only physical quantity, because spin of a proton is actually scheme independent quantity. The independent components are all scheme dependent. So if you see there is crisis, puzzle and things like that related to the individual ones, you should take it with a pinch of salt actually, because they are all defined in a particular scheme, they are extracted in that particular scheme, and the values are because of the scheme that you choose. Okay, and they have no physical meaning actually. I hope I made it very clear. So neither coupling constant nor PDFs are not some physical quantities like human being walking. Okay, they are mathematical constructs, they depend on the scheme. Somebody uses different scheme, it will look very different, evolve differently, and form of the function also could be different. I'm making it very dramatic, but that's the fact of life actually. So the interpretation of all these contributions from individual components depends heavily on the definition of this quantities. Okay, so now I'll just summarize that we can sensibly calculate hadronic cross section, okay, and that cross section would contain PDFs and calculable part, okay, and this PDFs, even though we don't know how to calculate them, but we can tell how they evolve. This part you can calculate, okay. Now, the most important part at this stage is to check whether this formula, okay, is consistent with experiment, okay. And in the beginning of the course, I said actually, Bjarken showed there is a scaling for this cross section. Now you see that after including all these corrections, okay, scaling is no longer there because there is this dependency on the scale q square explicitly. Not only depends on the scaling variable z, it also depends on the scale explicitly q square. So scaling is violated actually, okay. If you bring in interaction QCD, so deep inelastic scattering cross section now becomes scale dependent. Scaling is violated. Only at infinite energies, the AS becomes 0. This AS also becomes 0. This entire term drops out. Only delta function remains. So scaling is exact only in the infinite energy. Otherwise, scaling is violated. How it is violated? It is violated logarithmically, right? So scaling violation is logarithmic, okay? Now if you plot this cross section as a function of q square, it will give you a slope which is proportional to PQQ, okay? And if you can actually verify this experimentally, for every value of z, that slope is exactly what this theory predicts, then you can say QCD is the right theory, okay? And that exercise was also done, okay? You showed a plot where, there are slopes, lines going up, you must have seen, and the slopes of those lines, okay, will correspond to this PQQ z, okay? The scaling violation, which was observed in the nature or in deep inelastic scattering experiment, are consistent with this formula that I have written down here. They are according to this, this tangents, PQQ of z and PQG of z. So we have a very successful, model or a theory which explains everything that we know of actually so far. There's nothing we can claim that QCD does not explain, that we need to go to theories beyond QCD actually. Okay, so with that I'll stop, and if you have any questions, comments and things like that, you can always write to me. My institute, in my email address you can find out in my institute webpage, ravindran@imsc. Okay, so I'm really happy that I could share some of the things that are very close to my heart. Thank you.
Thanks, Ravindran.